Okay, so yeah, my name is Elisabetta Chicca from the University of Groningen. I'm going to talk about neuromorphic insight-inspired navigation. So we're going to change gears at very different levels. We go from human, macaque, and mouse to insects. We look at something called neuromorphic systems, but we also change gears in terms of the neural network. So we do the other direction of the approach. Instead of training a very complex deep neural network and then looking at the principles that emerge inside the network, what we do is the other way around. We identify principles from biology, and we use these principles to construct our very specialized network without their learning at this time. So let's go into the outline. I want to first tell you a few words about my group and use this opportunity to also introduce a bit what I mean by neuromorphic. Then, as I said, I'm gonna show you a very specialized network that does navigation in a way that is inspired by how insects do navigation. So also in this talk, there's going to be an agent that can operate in real world, but also in this talk, we're going to have the same agent simulated in a virtual environment to be able to acquire a lot of data to characterize the performance of our system, of our agent. Okay, let's start with the group. Oh, sorry. First, I want to say that going through these topics, I want to keep in mind the question of today. So what can computer vision learn from visual neuroscience? And I try to go back to this question in between the talk, but also, of course, at the very end. Now let's move to the group, bio-inspired circuits and systems. So what we do is fundamental research. So our core research is really about emulating neural functions in full custom CMOS systems and more lately into hybrid memory CMOS systems. So we use really the original definition that was given by Carver-Mead of using the physics of the device for implementing biological functions. But of course, we also take advantage of systems that are based on digital processors, that they can do simulation of neural network. And this is very useful for us to do fast prototyping of ideas, because as you can imagine, building systems into this kind of framework, it's very time expensive and also money, and also money, it requires a lot of money. Sorry, I'm in the wrong time of the day. Okay, so we put all of this together in basically two streams of research. One is really looking at systems and theories for brain-inspired computation, where we put a lot of focus on learning, on biologically reasonable learning. And at the same time, we do research on sensing and actuating. And for the talk of today, I'm going to talk about sensing and actuating. And of course, all of this research couldn't happen if it wasn't for the amazing people that are working on it. And in particular, the talk of today is presenting the work that was done by Torben Schopen during his PhD. Okay, let's start with insect-inspired navigation. This is the diagram of our network. You don't have to try to understand it now, but I will go through it piece by piece by just showing you the main concept that we implemented in this network and how they operate in realistic tasks. So let's start with optic flow. And for doing that, we start with how we do vision at the sensor level. So the first thing we want to look at is clock-driven versus event-driven sensing. And so now I want to introduce you this concept. And the first one is clock-driven sensing, which is very familiar to you. So you have any variable that you're sensing in the world. This is changing over time. And what traditional systems do, they slice time. So you have a clock. You have to make a decision on how often you want to sample this variable. And then if you think about vision, every time you sample the variable, you don't have only the data point of that particular pixel, but you get a full frame. So you get a collection of of digital words that represent your image. The problem you get with that is that when things are not changing, you get redundancy. You get a lot of data that is not useful because the input didn't change. At the same time, you get also information lost when things are going to change very quickly. So now let's see what event-driven sensing does in contrast to clock-driven sensing. And that's what you see in this figure. Again, we have time. Again, we have the function that we are observing or the data that we are sensing. And now the slicing happens horizontally. So we decide in this case that we sample the data only when there is a change of a given amplitude. And that's the value that we fix, the amplitude of the change for which we want to acquire data. And what you see in this case, in contrast with the previous example, is that there is no redundancy when no change happens in the input, but at the same time, we're able to do fast sensing and adapting the frequency of sampling to the dynamic of the signal. The redundancy is suppressed twice because not only we don't acquire data at this particular pixel if we are thinking about vision when nothing changes, but we also do the acquisition of the signal in a pixel-based manner. Therefore, we get rid of the frame concept and we eliminate redundancy twice. Okay, again, the question of today, what can computer vision learn from visual neuroscience? The message here is really that for some tasks, it would be better to learn from neuroscience starting at the sensing, because event-driven sensing is inspired by biological sensing. And by doing that, as you already saw, you can gain a lot in terms of making your data sparse from the sensor. And you can have very fast reaction to changes in the environment. Okay, now if you acquire data this way, and if you look at visual data, what you see is images of this kind. So this is the output of an event-driven visual sensors. The data was provided by Toby Delbrook. And this is what you see coming out of this sensor when you have it on a car and you are driving on the street. So what you see is the edges of objects that are moving in your visual field. And now you can think about this and you can think about self-motion and how self-motion is used to perceive the relative distance of objects. So you're all familiar with the situation of sitting on a train and looking outside, and you can easily recognize that in this situation, objects that are close by are going to move very fast into your visual field, as the trees here. But the hills far away and the mountains here, they're going to move very slowly in the visual field of the observer. This is a very well-known mechanism that is used by insects to navigate in the environment. So they estimate the motion flow in their visual field, and they use that to avoid obstacles. So what we did in this context is to create a so-called spiking elementary motion detector, inspired by the classical elementary motion detector, but encoding things with spikes from the sensor. And then what happens here is that if you have 2 pixels, you have an element that is computing the time difference between the activation of the 2 pixels, which is going to give you an estimate of the motion flow, of course. So the shorter the time distance, the higher the motion flow. So we were able to develop a neural network that uses this kind of motion flow estimate to let a robotic agent navigate into the environment without hitting obstacles. And now I have to switch the courses. So this is our robot. And this is an experiment that we did in view of doing similar experiments to what is done with insects. So tunnel flying, here we have a corridor instead of a tunnel because we're not flying with our robots. But you can see that simply embedding this kind of function, so avoiding obstacle because of option flow estimate, the robot is naturally able to center a tunnel, but also to navigate in more realistic environments. Let me get the cursor again. And of course, then you can do a quantitative evaluation of the performance of these agents. So you can do, for example, the corridor experiment, both in a narrow corridor and in a large corridor, as you can see here, and you can evaluate the performance of the agent. But as you might know, these kind of experiments in real world with a physical robot are time demanding. Therefore, we also created a simulated version of our robot, and we do experiment in a simulated environment where then we can try many more environments and many more tasks. And for example, here you see navigation in a cluttered environment. And you see that the robot is in this phase still driven by noise. There is no goal direction. Therefore, you see the red trace here is the path of the robot, while the blue squares are obstacles. And so given that there is no goal direction, and there is noise introduced into the system, if there are no many obstacles, the robot is just going to perform a random walk inside this virtual arena. As the obstacle density increases, the robot is forced to identify corridors in which it can travel without colliding into obstacles. And as the density of obstacles increases even further, there are no corridors available for the robot to navigate. Therefore, the robot is going to stay in a closed region next to the initial position. Okay, now let's add some more ingredients. As any agent, the robot needs an information about how it is moving into the environment and what is position into the environment. So again, by looking at the insects, we know that some of them use a polarization signal to have an estimate of their orientation in the environment. But you see also this arrow coming back here, and this is the error signaling that proprioception is, of course, an important aspect of keeping track of where the agent is going, or the insect in this case. So I'm not going to go into details, but we augmented this model by introducing proprioceptions for keeping track of motion direction, and we enhanced this keeping track of motion direction with the knowledge of polarization. And here I just show you very quickly that our spiking neural network, you can see here its activity over time, that is keeping track of the angle of the agent, where you see that the activity of the neurons in black are really following very well the angle measured. So let's move to the next piece of the network, which is related to the fact that now the agent might have a desired direction, as indicated by this arrow. A desired direction can have many different meanings. For example, in bees or ants, you can think about the homing direction. So it can have different meaning and can come from different places in the brain. And of course, at this point, once this information is available, what you need to do is estimate the difference between the desired direction and the actual direction that is coming from this internal compass in the brain of the insect. So we added another layer that is performing this difference. And also in this case, we look at insects, and in particular here, we took inspiration by the work of Yu et al., where they look at how Drosophila can keep track of the difference between a desired and a current direction by computing with vectors. So there are neurons in the brain of the Drosophila, in particular in the fan-shaped body, which can do vector computation and calculate the error in terms of desired and actual direction. So we made a very simple model in which we have a ring of attractors that encode either the current or the desired direction. And for the current direction, we have force-shifted version. And this force-shifted version can be compared with the desired direction. And the outcome of this comparison, you can see it in the four replica where you see the activation of the 5 networks. So the one on top is the current position and the one below is the desired one. And what you see is that if you compare these two activity, you will get activation here in blue, which is going to tell you, I mean, it's going to tell the brain of the insect, or our model in this case, if it should go forward because there is no correction needed, or should do a left turn or a right turn or a 180-degree turn. And this is encoded in the blue activation of the neurons. So we put also this into a spiking model. And the first thing that you can see is that here you have, again, a simulated agent in a virtual arena. So these are this is the virtual space. And because we provide a fixed goal direction, of course, the robot is going to go straight. And it's doing quite a decent job into going in the direction that is provided to the agent. But this is kind of too clean and too far from biology, and you can imagine that is going to lead to problem. And this is clearly seen when you start thinking, okay, let's put something in the arena so that, yes, the desired direction is here, but there is a wall here. And so this kind of implementation, it's really too simple to be able to then overcome this wall. So keep in mind that the obstacle avoidance is already into the network. It's not that we're not doing obstacle avoidance, but the drive into the desired direction is too strong, such that even though the obstacle avoidance you see here is really doing its best to keep the robot away from these walls, the desired direction is winning and making it crash into the wall itself. So again, a nice way in nature to escape a difficult situation is to explore, and we motivate the agent to do this exploration by adding noise into the system. So now, even without the presence of walls, you see here the same experiment here, but with some noise introduced into the system that is trying to keep the direction. And now you see that on average, the system is going in the right direction, but it is meanwhile also exploring a little bit. Of course, this has some cost, but at the same time, it has the gain value that in a more difficult situation where there are walls, the robot is able most of the time to avoid the walls and then later on direct itself into the desired direction. Okay, so also here we can do quantitative characterization of this behavior. And in this particular example, we can repeat many experiments with different obstacle density, as I showed you before for the obstacle avoidance. And here you can see 3 different experiments at low obstacle density, where the program desired direction was this one. In this example, the program desired direction was this one. And here I don't remember, but you don't really see it from the simulation, because here, as in the example before, there are so many objects that the robot cannot just go in the desired direction. But good news is that it's still able to not bump into the objects. Okay, then you can characterize this kind of behavior. And of course, what you will see is that if you look at performance success rate, you can measure it by repeating the experiment in the previous slide many times. And of course, you have 3 different conditions. You have the collision of collision. The robot is still not perfect and does sometimes make collision. This is a failure in this case, but then there are 2 conditions that are both signaling success. So either the robot is able to leave the arena because it could follow the desired direction, or we have to set a time over for the simulation, because there are situations in which the robot would run forever. So these 2 conditions are success, and here we plot the success rate as a function of obstacle density. And if the task is very easy, so this obstacle density is very low, the robot is very successful and can perform at 100% success rate. But as expected, you see that the success rate goes down as the obstacle avoidance is increased. So we're close to the end of the time available. Therefore, I will wrap up here with conclusions. So what I showed you in a very superficial way because of time available is that a complex system with animal-alike behavior can emerge by combining local neuron units in bio-inspired architecture. This architecture is implemented in a distributed, parallel, and asynchronous neural system, robustly performing biological relevant tasks in closed-loop experiments. And you have to know that this system is spiking from the sensor to the motor. I didn't go into the details of that, but you should be aware of the fact that we did tuning of parameters, only one, basically to allow each local neuron unit to perform the desired behavior. But then different tasks were performed in a variety of environment with a single set of parameters. And this is, to me, a good indication that by doing this kind of research, we are able to identify robust computational principles that can work together into an autonomous agent. And then again, what can computer vision learn from visual neuroscience? So I think here there was a bit more than only computer vision, but you might get a hint that for some task closely replicating biology, it's first of all very useful for understanding the principle that biology uses. But as a side effect, you also have potential of developing technology that is really complementary to the traditional artificial intelligence approach and can have an impact, especially when limited resources are available to the system. And let me, of course, acknowledge the people that were involved in the work, the funding agencies, and the platform that we use, and also the Capocaccia Cognitive Neuromorphic Engineering Workshop, because some of the work presented here started at that workshop. And of course, thank you for your attention.
Thank you, Professor Chicca, for your great talk. So is there any question?
See a lot of hands in the Zoom.
Jeff.
Yeah, I have a couple of questions, one kind of specific and then one very general. So the specific one was, it seemed like to solve the problem, you added noise and that got you towards the desired location. But what if you added something like time to contact, which I think there is a signal like that in insects to kind of wait when you're going to avoid obstacles versus when you're going to go to a goal. Do you think it'd be a smoother?
Where would you add time to contact in the obstacle avoidance part?
Yeah, I mean, there must be a weighting between how much you rely on the desired goal and how much you rely on your obstacle avoidance without knowing.
Yeah, so in the obstacle avoidance part, we don't really have time to contact because we do motion flow simply and we don't really estimate the distance of the objects. So that information is not available to our system, but you're right, you can find different ways to modulate the drive of the obstacle avoidance network and the drive of the goal-directed network. And there are different ways of doing that. In this case, we added noise to the part that follows the goal. But we have different systems in which we did, for example, something in which we were trying to reach a sound source. And also there you could modulate, the strength of the two. And in that case, we didn't add noise. So it depends also on the full system that you have available. But in terms of time to contact, we don't have such information available in the system.
Okay. And now my general question, that working in neuromorphic engineering is very complicated. I don't know if people realize all the stuff that goes into the decision making, but I get asked a lot and I don't have a good answer, like from other people, like how can I get involved? How can I try out some of the ideas I have on neuromorphic systems? Do you have any advice for people like that?
So here in the beginning, I had this thing about the platforms that are available. Here, I only have these two examples, the Spinnaker system and the Intel from the Lohi system from Intel. So those are two starting points, I would say. It really depends how deeply you want to get your hands into the neuromorphic field. Of course, you wouldn't start from here. You wouldn't start from designing CMOS systems, and you have anyway to have a very good reason to do that. But if you don't have access to this system, and I mean, one of the peculiar thing of neuromorphic systems is that often they rely on spiking neural networks. So if you don't have access to this system, a very user-friendly available tool is the Brian simulator, for example, and there are others, but start with simulators of spiking neural network to just get an idea on how you can test networks architecture and things like that, if that goes a bit in the direction that you were thinking about.
Yeah, no, that's very helpful.
But yeah, or get in touch with me if you want to.
And you
to do
mentioned
something
Capo
else.
Caccia, and also I think there's Telluride too. So
Capo Caccia and Telluride. Yeah, Telluride I normally have in the last slide, but the particular work I selected today, it was done by Torben, and Torben never went to Telluride, so it would have been unfair to acknowledge Telluride here. But that's another place where you can also get involved and be exposed to the community. So these are the two main events, and the nice thing about them is that you really end up working with people during these events. Yeah, COVID allowing, because the last Capo Caccia, unfortunately, there was a COVID outbreak, and so things are complicated nowadays. But yeah, of course, those are the two places to go if you want to know more.
Okay, we have a couple of more questions. Emily, if I pronounced your name right.
Hi, thanks. Okay, I had a question about the neuromorphic hardware that you use to continue the previous question. Those are really interesting results that you have, and you said you implemented this and experimented with this on Spinnaker. Is that it?
Yes, this particular system we did it on Spinnaker, but we also use Lohi, and we plan to transfer it to Lohi.
Okay, and so to use Spinnaker, which specific board did you use, like Spin 3, Spin 5, and because I'm really interested in the size of the architecture that you use to have those results.
Yeah, so the obstacle avoidance only is like 4K neurons and 400K synapses, just to give you an idea. But I don't have the updated numbers of the full system, because the results I presented today about the full navigation system are quite recent. So I didn't have time to ask Torben about the numbers now. But those are approachable numbers. They're not ridiculously high. And so we have both the small and the big board, but as you can see on the robot itself, I think, oh wait, maybe I have a backup slide, but I don't think I have the mention of which board. No, it doesn't mention it, but you can see it here.
Yeah, it's a small one, I believe.
It's the small one. On this system, we use the small one, yeah.
Okay, nice, thanks.
You're welcome.
Michael? Yeah.
Hi, Elisabetta. I'm so happy to see you, though I'm sad it's not.
Me too.
Can you explain a little bit more how you did the parameter tuning? I remember that being the most painful part of working with the system, and maybe there's a role for on-chip learning instead.
Yeah, so the most painful part, yes and no. I have to admit that by now Torben is an expert in doing that, and I have to admit that we did it totally manually. We don't have any automated procedure for doing that. Good news is that we rely a lot on winner-take-all networks and ring attractors. And once you become a bit familiar with them, you know how to operate them, and you know the regime in which they operate well. And good news is that they are robust. So it's because of this competition among neurons and so on, they're quite robust. So it's not that if you change a bit one parameter, they're gonna collapse and stop working. Yes, of course, automated way and learning and learning could be one of them, to tune parameter are very interesting. Torben has been tempted by doing it several times during his PhD. By the way, he's now writing his PhD thesis, and he's gonna finish soon. And now he wants to do it in his postdoc, so he's gonna join the group of Emre Neftchi. And one of his goals there is to look into learning as well. I have to admit, in this particular system, I don't see the need for learning so far. I mean, I see the need for automatic procedure for tuning parameters, if you like, just to scale up the system in a more efficient way. But the tasks that we have been approaching so far, they don't need learning. So we do, in the group, we do work on learning a lot. So far, we have done it in other contexts, and I'm really, yeah, I'm interested to bring the two things together. But I have to admit, with the task we have evaluated so far, there is no obvious need to do the learning. But by learning here, I don't mean parameter tuning. I really mean, yeah, that there is a recurrent neural network with synapses that modulate their weight depending on experience and so on.
Thank you.
Welcome.
We have one more question. So the next session is a break session for 30 minutes. So I think you can keep on asking because it's a break session, and not only to Professor Chicca, to also the other speakers, Professor Arun and Lindsay, if you have questions during this half an hour. So Tran, you can ask your question to Dr. Chicca. And the in-person audience, so we will take like a half an hour break, and then we'll be back.
Thank you.
Tran is gone.
Oh, sorry, I'm here.
Oh, you're back. Okay.
Sorry.
You can ask your question if you like. No problem.
Thanks for your presentation. I would like to ask what happened when we have movable obstacles and how can we deal with it? How can we deal with it? Yeah.
This is a very interesting question that we haven't analyzed. First of all, our sensor could stop seeing them if their velocity is the same as the agent, because in that case, they would not generate a change of luminance over time at the sensor. So it's kind of tricky. We haven't done any work in that direction. The interest there, it goes, I would say, in another direction. If you think about prey catching, we have amazing examples like the dragonfly. And there is exactly this problem of tracking an object that is moving while the agent itself is moving. And so it is in my list of things to explore. And also in that case, I would take a lot of inspiration from biology and try to understand how the dragonfly does it. There is a lot of research in that field, both from the neuroscientists and the people doing the modeling. So that would be for me a very fascinating problem, but yeah, we haven't looked at it. And for our specific task, it's normally not a big problem because the chances that the moving object is moving, yeah, I mean, so far we haven't, yeah. I'm thinking while I talk, so I'm not operating very well.
I understand.
We haven't done it, and it could be tricky, but in some environments is not a big problem.
Okay, thank you.
You're welcome. I think it was a very unsatisfying answer.
Yes.
Any other questions?